let's learn a little bit about the gradient. And we'll use the same function we've been using since we're pretty familiar with its graph and its partial derivatives. So let's say that f of x, y is equal to x squared plus x times y, or I could restrict xy, plus y squared. Now we're going to take the gradient of this, and then I'll give you a little bit of intuition on what a gradient is. We're going to take the gradient in two-dimensional space, and you'll see what that means in a second. You can extend this to any dimension. So the gradient, and we use this vector differential operator, this upside down triangle, the gradient of f is equal to the partial of f in the x direction times the unit vector I, which is the unit vector in the x direction. So it gives the magnitude of the slope in the x direction, and then that's the magnitude, and then it points the vector in that direction, plus the partial with respect to y in the j direction. And obviously if there was a function of more variables, you could keep going, and you would multiply the magnitude of the derivative in each of those directions times the unit vector in that dimension. Anyway, well, what does this mean? And another way to view it, you could have also written this as the gradient of f is equal to the partial with respect to x of f of xy, and then all of that in the I direction. This is just a different notation, plus the partial with respect to y times f of xy, not times, operated on f and xy. So the partial of f of xy with respect to y times the j unit vector. And because of this notation, a lot of people view this delta operator, and actually is pretty consistent when we learn about the divergence and the curl. A lot of people view this del operator, they actually define it. They say that is equal to the partial with respect to x in the I direction plus the partial with respect to y in the j direction. And then if you wanted to do it into 3 space, and I'll do that kind of in a... That's not going to apply to our problem because we only care about 2 dimensions right now, and you'll see what I mean, because even though we're applying it to a 3-dimensional surface, but then you could do the partial with respect to z times the k vector, and then you could extend it to n vectors, but then it becomes n dimensions, but it becomes very hard to visualize. Actually, it becomes hard to visualize beyond what we're doing right now. But, so what does this mean? Well, it's... well, before I go into what it means, let's actually calculate it for this, and then I will show you what it means. So what is... Let's actually calculate let's actually calculate the gradient of f. So the gradient of our particular function, it's the partial with respect to x. So we figured that out. That's 2x plus y, and then that doesn't matter anymore. So it's 2x plus y. That's the partial of this function with respect to x. And we multiply that in the I direction, or in the x direction, plus the partial with respect to y, and this is 2y plus x, 2y plus x, and we calculated this in the 2 videos on the partial derivatives, and we multiply that in the j direction. So what does that look like? Well, what are each of the components of this vector look like? What is 2x plus y in the I direction? What does that vector look like? What does 2y plus x in the j direction look like? And this I have graphed. So this is the same surface we've been working with, but now I've plotted these points right here. These are just points that the software has picked to actually display these vectors. And if you look at it, this is the x-axis, and I can rotate this. Let me pull it down a little bit, and then I can spin it around. I think that's pretty neat. But anyway, this parallel to this line is the vector in the x-axis, right? So at this point, I've actually calculated the gradient. This vector says what is the magnitude of this vector is the partial derivative of the function, or the partial derivative of the surface, or the partial derivative of z with respect to x. And its direction is it just goes in the x direction, right? Because it's that times the I unit vector. So this vector is the partial derivative of z with respect to x times the I unit vector at that point. So we just calculated the partial derivative at that point. It gave this length. And then the direction is just the I unit vector, or in the direction of increasing x. Similarly, this vector right here, I hope you can see it. Let me see if I can actually zoom in a little bit. That might be useful. Zoom in. There you go. This vector, and just so I wanted to see the axes, which you can't see now that I've zoomed in, but you took my word for it. This was the x direction. Now this is the y direction, or the same direction as the j unit vector, right? The j unit vector goes in the same direction as y. And the magnitude is determined by the partial derivative of z with respect to y at that point. And that's the magnitude. And we saw there was some symmetry, so the magnitude of this vector is the same as the magnitude of this vector. And then when you add the two vectors together, you get this vector. And notice that none of these vectors have any dimensions in the z dimension. They're all kind of giving you directions in the xy plane. And why is that interesting? Well, the gradient, and this is the intuition, the gradient tells you the direction in the xy plane you should travel in order to get the maximum slope in the z dimension. Or another way to view it, remember the partial derivative with respect to x said what is the slope in the x direction. The partial derivative with respect to y said what is the slope in the y direction. But you could take the partial derivative with respect to any direction, and the gradient gives you the direction in which the slope is the largest. So let me zoom out a little bit, just because I want you to see the actual axes. There's the axes. So all this says is if I were to go in this direction, I get the maximum slope. So if I go into this direction, my z goes up like that, right? Let me see if I can rotate this a little bit. I don't want to scale it anymore. Let me do the rotate it. Let's see if I can show that to you. So if I go in that direction in the xy plane, I get maximum z. So if I go in that direction, I get a maximum upward slope. That's what the gradient tells you. How do you get the maximum upward slope? And if you were to take any contour, or I guess you could say any closed line where the z is constant, well actually I don't want to get into that too much, but this gradient will actually be normal to any, or it'll be perpendicular to any curve where z is constant. I don't want to get too involved in that right now, so let's go back here. So maybe it's more clear if you look from below the graph, right? So if you go to this point right here, this is the magnitude of this vector. Shows what is the slope in the x direction. The magnitude of this vector is what is the slope in the y direction. And then when you add them two together, you get the gradient. And the gradient says, well, if I travel in this direction, in the xy plane, notice that none of these have any z's, right? The plane defined by all of these vectors, it's all flat in the z dimension. But if I were to travel this direction in the xy plane, then I will get the maximum increase in z per unit that I travel. And let's actually show you what it looks like in the xy plane. So if I just go head on, so I'm above the graph, looking straight down at the graph, and then the colors just show kind of where we are. But if we're down here, if I travel in this direction in the xy plane, I get my maximum increase in z. If I'm here, and notice here the x component of the gradient is much larger than the y component. So I need to travel a little bit more in the x direction, and I'll get the maximum change in z if I travel there. Another way to think about it, if I'm on a hill, the gradient of that surface will tell you at any point what direction you need to travel in to go up the hill fastest, or the direction which the steepness of the hill is maximum. This is more of a bowl as opposed to a hill. But anyway, I'll just rotate it around. Hopefully that makes some sense, and I want you to think about it a little bit more. And we'll do a few more problems where we just calculate gradients, just because I think it's useful to get the mechanics. But in my opinion, at least, the intuition is a little bit harder to get your head around than the actual mechanics. But once you get it, it makes a lot of sense. I will see you in the next video.